Paper 4-1.
May, June 2023, paper 41. Question 2.
Okay.
Question already completed.
All right.
Okay, question 2. A steel sphere of mass 0.29 kilogram is suspended in equilibrium from a vertical spring. There's a vertical spring. The center of the sphere is 8.5. Right, center is 8.5 from the top of the spring, as shown in the figure. The spring is now set in motion so that it's moving in a horizontal circle at a constant speed as shown in figure 2.2. The distance from the center of the sphere to the top of the spring is now 10.8 cm. Explain in reference to forces acting on the sphere why the length of the spring in figure 2.2 is greater than figure 2.1. Okay, you can draw the picture to understand what's happening. There's your weight mg, there's your tension T. Okay, previously it's the tension in the spring equals to the weight. Now the tension has to support the vertical component of tension balance the weight. Horizontal component provide a centripetal force. Right, so that's why now T is greater than your previous value. Horizontal force on the sphere causes centripetal acceleration. Weight on the sphere is now equal to vertical component of tension, or horizontal and vertical component of forces now combine to give a greater tension in the spring. Greater tension in the spring, so greater extension in the spring. Okay, can I understand?
Yeah.
Hey, what is happening? Something went wrong. What's the matter? Why is it? We are basically looking at this picture. Looking at this picture. So we are redrawing it. Right? There's a weight. There's a tension. The angle between the axis of the spring and the vertical is 27 degrees. So that the radius is 0.49 cm. Let me just get a picture there. Okay, that's the picture. Right, so this one is just the forces acting on the picture there. So we can redraw this triangle, right, where there is 10.8 cm. This angle is vertically opposite angle, 27 degrees. There's your R, there's your R. So R is just 10.8 sine 27, and calculate out. So the tension, the spring is 3.2. So we can still use this triangle, right? Where this now represent the tension. Tension there, T, the one we represent the weight mg, and this represent the centripetal force. So mg right? The mass is 0.229 times 9.81. So we got 2.884 Newton. Then we know mg. Want to find your tension there. So cos 27 is mg over t. So t is just right, cross multiply and then take your calculator, calculate out 32, 3.2 Newton. The spring obey Hooke's law, calculate the spring constant. This is your AS work lah. You should be able to do that lah. Right? 10.8. Previously is 8.5. When it's not swinging, it's 2.3 cm for the extension. So it's force over extension. This 3.2 minus 2.84 is 2 divided by 2.3 Newton per cm. Okay, 0.16 Newton per cm. I don't know why he gave 0.15. Use your information to determine the centripetal acceleration of the sphere. Right? And use the centripetal acceleration is this way, this one. So F equals to 3.2 is your T, sine 27 is 1.45. A equals to F divided by M. And your AS work. Okay, any comment? Mark yourself.
Okay.
Calculate the period of the circular motion. Right? We have calculate acceleration. We have given the radius. So we can use the formula, centripetal acceleration. Right? Subject W, omega. Right? 5 is A. R is changed to meter. So it's 10.1 radian per second. Then T is 2 pi over omega. So it's 0.62 second. Any comment? Or anything not clear? Okay, let's carry on. State the reason why two objects that are at the same temperature are described as being in thermal equilibrium. Yep.
No net thermal energy transfer and same temperature.
No net thermal energy transfer between them. Same temperature given already. Figure 3.1 shows the variation with temperature or the density of mercury and water. Temperature may be measured using variation with temperature or density of the liquid, such as why for measuring temperature over the range, mercury is a suitable liquid over 0 to 100 lah. Yep. What is the reason?
Variation of density with temperature is it's the same throughout.
It's a straight line lah.
No, yeah,
Basically,
linear.
there's only one reading. Whereas this one, if you use it for temperature around here, you may have this two same density. You don't know which temperature is measuring, so it's not good. This is a poor thermometer, water. Variation of density with temperature is linear, or each temperature has a unique value for density. This one has a unique value, this one has two values, so we don't know which one to use. Water is not a suitable liquid. Yeah. What's the reason?
Not variation with temperature is not linear.
Variation with temperature is not linear. Okay. Always remember 2 mark. You answer 1 mark, you get 1 mark only. 1 point, 1 mark only. Region where density does not
Region.
vary with temperature. Different temperature have the same density. Right? Any of these two, 2 point. A beaker contains liquid of mass 130 grams. The liquid is supplied with thermal energy at a rate of 810 watt. The beaker has a mass of 12 grams and specific heat capacity of 0.84 joule per gram per Kelvin. The beaker and liquid are in thermal equilibrium with each other all the time and are insulated from the surrounding. Show that the variation with time t of the, okay, that's a figure. State the boiling temperature in degrees Celsius for a liquid. Yep. What is the boiling temperature? Yep.
Um, is it like
What is it? Can
20? Hey, no, 80. Sorry.
80? Where is horizontal?
Yeah, 80.
This is boiling point. 80. Each of these is 2.5. Each small square is 2.5. Determine the specific heat capacity in joule per Kelvin of the liquid. Right? Q is PT. Right? There's a P. Right? There's a 21 second. So there's an energy supply. Q is MC delta theta. 170 is this one is beaker times specific capacity, and this is liquid times the specific capacity. Change in temperature is 80 minus 25. Right? 80 minus 25. Can any point not agree with me?
Yeah. Okay.
Okay, great.
Yeah, just take like the thermal energy gain by beaker plus thermal energy gain by water.
Yeah, because thermal energy supplied to water. Okay. The experiment in C is repeated using water instead of liquid. In C, the mass of liquid used, the power supply, and the initial temperature are all unchanged. The specific heat capacity of water is approximately twice of the liquid in C, and the boiling temperature of water is 100 degrees Celsius. On figure 3.2, sketch a variation with time of the temperature of the water between 0, t equals 0 and t equals 60 seconds. Numerical calculations are not required. So we go to the basic theory, right? This is thermal energy supply. Is mass of water times specific capacity of water times the change in temperature. Then take this one down, not that. Then take this one across there, we got this equation. So this is a gradient, right? Temperature against time graph. Sketch a straight line diagonal from 25 to 100 degrees Celsius to 25 to 100 degrees Celsius, and then a horizontal, 100 horizontal, which we have correctly. Straight diagonal line at 25 degrees with gradient approximately half that of the original. Okay, it depends on the specific, that is double. Mass is the same, so it's half, no? The gradient is about half, no? So you just take this roughly, no? Roughly half, no? Half of this length, no? Can
Okay.
say two basic assumption of kinetic theory of gases, okay?
Uh, no intermolecular forces.
1 point.
Random. They move. And you say they move randomly, in
Yeah,
all
because
directions.
are in continuous random motion. Continuous
And
random
then
particles have negligible volume compared with the gas. Volume of the gas.
perfectly elastic collision.
Any need to only negligible forces between particles except during collision or condition perfect elastic collision. Time of collision negligible in comparison with time between collision. Right? Any two. An ideal gas has a amount of substance and the gas is initially at a state X, pressure 2P and volume V. The gas is cooled at a constant volume to state Y with pressure P. The gas is then heated at constant pressure to state Z with volume 2V. Finally, the gas returns to constant temperature at state X. Determine the expression for temperature T of the gas in state X in terms of N, P, and V. Identify any symbol that you use. Okay, what should I do? What equation should I use?
PV equals nRT.
PV equals to nRT, okay? Then we just replace it with 2P. Volume is still the same. N is still the same. Right? That's our answer. Where R is the molar gas constant. Right? That's the one that's not mentioned here. So you have to spell it out. What's this constant? What does this constant mean? Okay, now you're supposed to draw on figure 4.1, sketch a variation with volume of pressure for gas at, as a gas undergoes three changes. The state X is label Y states and X state. Okay, we are told that Y state cool at constant volume to a pressure P. So it's vertical line, no? That's your Y. Then the gas is then heated at constant pressure to a state Z and volume 2V. That's why it is 2V. Finally, the gas returns at constant temperature. So it's a curve. I can put arrow if you want to. That's the marking scheme. Okay. Any comment? Anything not clear?
Okay.
During the change of state from Y to Z, the increase in internal energy is U. They're given U. U. Complete table 4.1 to indicate for each of the three changes in state, the increase in internal energy of the gas, the thermal energy is transferred to the gas, and the work done on the gas in terms of P, V, U, and W. Okay, from X to Y, work done is 0, volume is constant, pressure is half, the temperature is half. We use P over T is constant. No? Pressure is half, temperature is half. No? Internal energy decreases. Okay, then use first law of thermodynamics. W equals to 0. Your internal energy decreased by U. So you put a negative sign there because the temperature decreased. So your Q is minus 0. So there's heat flowing out. Y to Z. Y to Z. Work done. Work done is just your pressure times your change in volume. Change in volume is 2V minus P. Okay? This is an expansion, so it's negative sign there. Then since your pressure is constant, we use this equation, no? V over T equals to constant. P is double. T is double. So delta U equals to U. So use the first law of thermodynamics. Right? Replace your Q as Q minus W becomes minus PV. Then from Y to Z, Y to X, sorry, T is constant. In this case, your internal change in energy is the 0. Change in energy equals to 0. So your Q equals to minus W. So there is a work done by the guest. And fill in the table. Can anything not clear?
Okay.
They don't want to see your working lah. They just want your answer lah. But you have to have the working there before you can get the answer. Part of the electric circuit is shown in figure 5.1. The circuit is used to produce halfway rectification of an alternating voltage or potential different V in. There's your V input. There's your V output. The output across the 14 kilo ohm resistor is V out. A component is missing from figure 5.1. Complete the circuit diagram in figure 5.1 by adding the circuit symbol for the missing component. Okay. We want the correct symbol for diode lah.
Yeah.
So it doesn't matter whether in or out lah. Right? Whether the arrow is pointing to the left or to the right lah. Capacitor C is shown in circuit of figure 5.1. State the effect of V out. State the effect on V out of including capacitor in the circuit. Okay, what's the purpose of C?
Smooth.
Smoothing.
Hello?
Yeah, smoothing.
Yeah, smoothing.
Right? Or V out is smooth. Figure 5.2 shows the variation with time of V in. Right? There's a V in. And figure 5.3 shows the variation of V out. Right? You should be able to read the period. The period. Determine the frequency of V in.
1 or 0 point. Yeah.
Right? It's a period of
25 hertz.
0.04. Then use the formula. Frequency is on a period. 25 hertz. Show that the time constant for the discharge of the capacitor through the resistor is 0.38. How to do that? Now you got 10 more minutes. Yep. How to show that? What is time constant equals to?
Wait.
Yeah.
Oh, you want the answer?
There's your V. There's your V naught. Right? There's your V naught. There's your after a time of 0.02. That's your time. Your V can read from the graph. Okay. There's 3.25 here.
0.0380.
And you find your time constant first. Then take the ln. Take this one down. And take ln. Then you get your equation there. Then time constant. Okay.
Okay.
Calculate the capacitance. Give unit for your answer. How to calculate the capacitance? You calculate the time constant. What is the time constant?
E equals RC.
That's all.
C equals TOR.
It's actually
Oh.
tau lah. Tau equals to RC. Then from there you can calculate RC. Lor.
It's what do you call it? Like,
Tau. Tau.
what's the
It's a
symbol?
Greek
What's the symbol
alphabet lah.
name?
Greek alphabet. Greek alphabet.
T, ah.
Then cross multiply lor, to get your C value. Lor. R is given 14 kilo ohm. Change it to ohm. Lor. Okay.
Okay.
On the circuit of figure pair 1 is modified so that it produces full-wave rectification of an input voltage, suggests the reason how V out now varies with V in, as shown in figure 5.2. Yep.
Um, being as a constant magnitude in both positive and negative.
V in is constant
V
magnitude
out does not vary with time.
in positive and negative direction. So V out is now constant. Or V out does not vary with time. Constant value V out. Right? Because basically you are turning the negative to positive, that's all. Okay.
Okay.
What is meant by magnetic field?
A region of space where the forces acts on a moving charge.
A region where a force acts on a current carrying conductor or moving charge or magnetic material, magnetic pole. Right? Either one. Okay, yeah, right. A long straight wire P carries a current into the page as shown in figure 6.1. On figure 6.1, draw 4 field lines to represent the magnetic field around wire P due to current in the wire. Okay, mark yourself. They are not evenly spaced, becomes wider and wider. Then using your right hand curve rule, right, you get the direction of the field. Okay, that's how they're looking for the 3 marks. Any comment?
Hmm.
A second long straight wire Q carry a current of 5.0. Right, that's the second one. Out of the page is placed parallel to wire Q as shown in figure 6.2. The flux density of magnetic field at wire Q due to current in the wire P is 2.6 millitesla. Calculate the magnetic force per unit length exerted on the wire Q by wire P. What formula to use?
So I use the F equals BIL.
That's all. And because BIL, you want to find force per unit length, right? Magnetic force per unit length. So it's BIL. So B, there's a B, change it to SI unit. There's a current 5. Right? This one will provide magnetic field on here. Okay,
Okay.
state the direction of the force exerted on Q, on wire Q by wire P. Yep.
To the right.
Okay. To the right. or unlike current repel lah. Flux density of magnetic field at wire P due to current in wire Q is 1.5 millitesla. Determine the magnitude of current in P. Explain your reasoning. Okay, force per unit length has the same magnitude by Newton's third law. VIL. I is F divided by L divided by 1 over times 1 over B. Okay, can
Okay.
change, remember to change it to SI unit. And F over L we have already calculated previously. Just put it inside there. Say what is meant by the Brody wavelength. Yep.
Electromagnetic wave.
Huh?
Wait, no shit. Electron diffraction.
Wavelength
Wait, sorry.
associated
Wait,
with
you had
moving
the
particle.
wrong question, I think.
Wavelength associated with a moving particle. Figure 7.1 shows a glass tube which electrons are accelerated through a high potential difference to form a beam that is incident on the graphite. That's the graphite crystal. There's a fluorescent screen. Inside there is vacuum. There's your anode. There's a collimator. Collimator is to keep it straight lah. Narrow beam of electron beam. Filament emits the electron. After passing through the graphite crystal, the electron reach the fluorescent screen. The screen glows where the electrons strike it. Figure 7.2 shows the fluorescent screen view here and on and the right hand side of figure 7.1. State the name of the phenomenon by the pattern shown in figure 7.2. What is the phenomenon? Anytime will be cut off already. Yep, what's the phenomenon?
Um, it's the electron diffraction, right?
Electron diffraction.
Yeah.
Explain what can be concluded from the pattern in figure 7.2 about the nature of electron.